to keep the traffic going. That sounds familiar, huh? Yeah. Right. Okay. Do you also light the firecrackers for celebration? You don't have that custom, huh? Good. I'm glad you don't do that. It's quite dangerous. I remember getting hurt quite bad trying to light the firecracker while holding it in hand and throw it at other people. All right. Okay. I think we can begin. All right. Good afternoon. We will review what was covered in the last lecture first. What we did last time was the topic of section 3.3, a quantitative analysis of the potential and surface potential in the silicon and the surface charge. What we really wanted is the charge. We started by solving the Poisson's equation, but we did not finish solving phi as a function of x. Instead, we solved the surface charge, or I shouldn't say surface charge, really the substrate charge, QS. All the charge in the substrate, this includes the inversion layer, if there is an inversion layer, the depletion layer charge, if there is one, and the accumulation layer charge, if there is accumulation layer, right? All those charges add together we call QS, the substrate charge. We found an analytical solution, or analytical expression of phi s as a function, of QS as function of phi s. So this is the substrate charge as a function of what? Of surface potential. Right? Phi s is surface potential, it's the bending the substrate. That's what we found. An analytical function, it involves exponential functions. And this review probably reminds you what equation we're talking about. Of course, I don't expect you to memorize that equation, but you should know there's such a function there if you need it, right? Okay. Next, we use the relationship that the small signal capacitance of the substrate is equal to minus dqs d phi s. Now, this may need a little bit thinking, getting familiar with this concept that indeed there's a capacitance between the interface and the neutral body, and that capacitance is called CS, and it involves charges contributed by the inversion layer, depletion layer, and accumulation layer. Okay, the equivalent circuit would look like this. We have a oxide capacitance in series with substrate capacitance. This defines the substrate capacitance. And this defines phi s, that's relationship. All right? Good. Try to think of this CS as a very real capacitance. And if we plot this capacitance, and since we know QS is function of phi s, therefore we know CS is function of phi s, right? We simply differentiate that QS once, we get CS is function of phi s. It's also an exponential function, even more complicated, involving a square root term. And if we plot that CS as function of phi s, we get this. This is the general shape. There are only two parameters in this expression. One is the doping concentration, NS or NA, or N, maybe you want to call two the parameters there, NA or ND. And the other is oxide thickness. All right, so those are the only two parameters. With those parameters, one can plot CS as function of phi s. Two special cases we'll look at last time is that at flat band, CS is not infinity. In other words, the capacitance is not equal to Cox. CS is finite. It's equal to epsilon s over LD. It's as if that the charge induced by the small signal voltage at flat band is distributed over a length of LD called Debye length. Okay? LD is typically a few hundred angstroms if we're talking about 10 to the 17th per cubic centimeter of doping concentration. At threshold voltage is another special case. At threshold voltage, CS happens to be equal to epsilon s over xd max over 2. Okay, we derived this last time, so this just reminds you what we did last time. It's as if the capacitance was due to the depletion region, but depletion region thickness was half of the xd max. A better interpretation is that we really have two capacitors at the threshold condition. One is epsilon s over xd max. That's the capacitance due to the depletion charge. The other is the capacitance due to the inversion charge, and it happens to give us the same capacitance as the depletion layer capacitance, and that's why we get a capacitance that corresponds to half that of the xd max. Okay, that's where we stopped last time. Any questions? Okay, if not, let's just do a few simple steps. 2 steps. One is we change the vertical axis from CS to C. C is this total capacitance, the two capacitors in series. CS put in series with Cox. So if you put CS in series with a constant capacitance called Cox, how would that total capacitance look like? Well, of course, it's going to be chopped, right? Eventually, we'll reach saturates at Cox. And that's what this looks like, yeah? Right? All right. So that's what we have. So now we have capacitance as a function, just kind of the shape that we expected before. In the accumulation region, it's equal to Cox. In the inversion region, it's equal to Cox. In the depletion region, it's the usual depletion capacitance. What's new is that in this transition region, now we have a smooth transitions. We no longer have to assume those sudden changes. So it's no longer a piecewise capacitance curve, but a continuous curve. The horizontal axis, however, is phi s. That's not what we like to work with, although this concept is very useful. Think about phi s all the time. It's an internal variable, in some sense, more useful than thinking Vg from the physics point of view. But from engineering point of view, we don't care about, from circuit, for example, we don't care about phi s. We want to know capacitance as function of Vg. So there's one missing step, that is to translate every phi s value in this left-hand side figure, change that phi s from every point to a corresponding Vg. So we need a relationship between phi s and a Vg. Can you think of a relationship that relates phi s and Vg? In other words, given a phi s, will you be able to tell what Vg corresponds to this phi s? Can you think of an equation that relates this two? The answer is this. Okay, that's why I ask you to memorize it. Vg is equal to VFB plus phi s minus Q over Cox. Remember that equation? That says Vg equal to VFB plus the substrate voltage plus the oxide voltage. Is that right? Now, why does this relate to Vg to phi s? Well, certainly phi s term is phi s. But this Qs term is also a known function of phi s. Is that right? It's a complex function, difficult function, but it's a function. So for every point on the phi s axis, we can write down a corresponding Vg value. That's how we end up with CV characteristics. Is it okay? All right? Any questions how to get CV? We first get C as function of phi s, and then we relate phi s to Vg. We end up with C versus Vg. Is it okay? Yes?
Can you define again what VFB was? Because in the book they just say Vg is equal to Vox plus phi s. But I think they skipped the FB part.
what textbook does is say it thinks it's easier for you to first assume there's no such a thing as VFB. I actually think it's complicated. Why bother with that, right? Let's just accept the fact that when we look at the energy band diagram, there's a condition called flat band condition, right? This condition, however, does not correspond to VG equal to 0. It corresponds to VG equal to VFB. That's VFB. So VFB is exactly what the name says and what you probably remembered from your first course in MOS theory. VFB is the flat band voltage. That's the voltage that has to be applied to the gate to make the bands flat like this. When bands are flat, phi s is 0, Vox is 0. And any time when VG is not equal to VFB, the difference will be taken up by phi s and Vox. So I did not assume VFB is 0, right? That assumption is unusual even for textbooks, so it's kind of could even be confusing. So I don't recommend you to ever drop that VFB, all right? I think our textbook is the only one that start with VFB equal to 0 assumption.
Question?
All right, yes.
When you compare the two plots,
Yes.
the increasing the slope is greatly changed, but what is the difference in the left side or smoothing part? What is the difference between the two plots?
You are comparing these two plots, is that correct? These two plots are supposed to be identical in as far as the shape of the, well, I'm sorry, it should not be identical because we're changing the horizontal axis. So of course the curve may be compressed, expanded, shape can be changed a little bit. So I take that part. I don't see difference here. What's the difference that you want me to comment?
The first difference is the increasing slope is significantly different.
Oh, I mean here?
Yeah.
Okay, very good. All right.
But what happened on the left side of the circle?
Okay, so the question is, should the shape of these two curves be identical? They do not have to be identical. All the relationship between these two curves is such that every point on the left, let's say A, there is a corresponding point on A here, right? A point B here, there's a corresponding point on B, right? For example, the minimum capacitance here should be equal to minimum here, which wasn't drawn accurately. It should have been drawn minimum equal. But the shape could be different because the axis is now stretched. You have to now think this as a rubber band. Phi s is not equal to Vg, right? We haven't talked too much about relationship between phi s and Vg. But why don't we take this opportunity to do that now? Let's think about the relationship between phi s and Vg over this range and over, say, this range where there's a transition from depletion to well, let's not do that. That's too complicated. To this range, all right? So range 1 and range 2. We know that in both range 1 and range 2, phi s and Vg are not equal. They're not even just proportional to each other. But what I want to ask you is this. Let's say, suppose I chose the scale such that 1 centimeter of phi s here is roughly the 1 centimeter of Vg, roughly speaking. Would you expect 1 centimeter phi s in this range roughly equal to 1 centimeter phi s of Vg here, or do you expect to be equal to only 1 millimeter of Vg here, or expect this to be equal to 1 meter of Vg here on this range 2? Do you see what I'm saying? At first you chose a range, a scale of Vg, such as 1 centimeter phi s here is roughly 1 centimeter here, roughly. That's the way I drew it, right? Given that's the case, with 1 centimeter, or let's say a 1 volt change in phi s, in the inversion region, if you want to change phi s by 1 volt, does that correspond to about 1 volt change in Vg, or what? You shook your head. That's correct. It does not. What kind of Vg does it correspond to? Small Vg or large Vg? 1 volt change of phi s in the inversion region. You see already inverted. Now you want to bend it by another volt. Bend in another volt. What kind of Vg do you have to apply? Right? Probably thousands of volts, right? Your oxide will break down before this happens. Is that right? So that is why this these two scales are not simply proportional to each other. So there's less stretching here, there's more stretching there, right? So that's why the slope, I actually deliberately drew this a little bit sharper than here, because this scale is, how should I put it? How does it work? I don't really know what to say anymore. I suppose that the point is that there's no reason to think the shape will be maintained. Okay? It's still roughly the same, because so happens where the scaling becomes very different is where the curve is flat. It's flat, so whether I stretch it out to a meter long or keep it a centimeter, it's still a flat curve. Do you see what I'm saying? Yeah? So here, roughly the shape didn't change, but there's no reason to think the shape will be identical. Did I make that clear? Yeah, okay. So roughly it's this shape. There's no reason to be identical. All right? Good. Those are excellent questions. Now you get a chance to see the relationship between phi s and VG and have a better feel for what they're about. All right? Good. This diagram, the next slide, is something you have seen. I just want you to remember again that this capacitance is made of three parts. There's inversion capacitance, depletion capacitance, accumulation capacitance. Altogether, we call that CS, and CS is in series with Cox. The inversion capacitance and accumulation capacitance, usually we don't have to carry both of them. If one is significant, the other is insignificant. All right? But we often have to carry two, that is depletion capacitance plus the inversion capacitance, or depletion capacitance plus the accumulation capacitance. Okay? All right. This capacitance CV curve, would you call this a high-frequency CV curve or low-frequency CV curve? If you call this low-frequency curve, the answer is correct. And later I'm going to say a few words about this, terminology, low frequency, how low is low frequency. But if we divided this world into two parts, low frequency world and the high frequency world, this is indeed the low frequency part. What does low frequency mean? And why have we just derived the low frequency CV? Low frequency simply means that QS is at equilibrium with phi s. In other words, if we change the band bending, if we change the relationship between EC and EF at the surface, we are changing the electron concentration at the surface. In other words, this QS and the phi s, or put it more specifically, let me tell you, it's really the inversion that's questionable. We're saying inversion charge follows the phi s the way we usually think, namely electron concentration is proportional to minus phi s over kT or something like that, right? I forgot plus Q phi s over kT. So if we assume this relationship is always held, which is what we did assume last time, and we usually assume this unless we state otherwise. We always assume things are equilibrium. If we assume this, then we end up with the equation we got last time, and then we get the CV curve. All right? What does equilibrium mean? Equilibrium means everything is simple, and you have left it there for a while. That's equilibrium. So therefore, it's more like low frequency. If we now start to change the VG very rapidly, there's a possibility that things are not at equilibrium. All right? So specifically, let me tell you why it would not be at equilibrium. For example, if we start at flat band, this is the band diagram at flat band, right? Phi s is equal to what in this drawing? Phi s is equal to 0. At flat band, phi is equal to 0. What is electron concentration? You don't have to give me a number. It's just small, right? Small electron density. Is that correct? Now if I suddenly apply a VG to bring phi s down to something like this, suddenly, very, very, very rapidly, within a nanosecond, I can bring voltage to VG to cause band bending. Is that right? Yes? Right? At that point, what do you think electron concentration will be? Do you think it will be 10 to the 17th that we would have expected from this equilibrium consideration? The answer is no. The reason is we don't have a supply of electrons. Here we have a lot of holes because N-type semiconductor, a P-type semiconductor, right? This is p-type sample, a lot of holes. We don't have any electrons. Electron density very small. Now within a nanosecond, we force the band bending to look like this. Where do the electrons come from? We will still have very few electrons. Isn't that right? Right? So there's a possibility that this relationship that we derived last time would not hold. Of course, last time we did not separate the charge among the three. All we know is the sum is this QS. So this relationship may not hold, specifically in the inversion layer. All right? The inversion charge will not follow what we derived last time. And when it does not follow, we get a situation called high frequency. All right? Let's put it this way. What does high frequency mean? High frequency means this. All right, we apply a DC bias to make the band bends like this. And wait for a while. Okay, wait long enough. Then do you say we will have the expected high density electron here, say 10 to the 17th? The answer is yes, right? If we wait long enough, we will have that. Now I make the problem more complicated. This is our DC bias. What if I now apply an AC signal at 1 megahertz? So I wiggle this band bending, wiggle this phi s a little bit, right? Will the electron density wiggle with this change in the phi s? The answer will be zero, no again, because there's no supply of electrons, right? This electron will not change at megahertz. No way for it to do that. And that's why if we apply 1 megahertz as the AC signal, we do not expect to find this CV curve. Instead, we expect to find we find a deviation in the inversion layer. In the accumulation layer and depletion layer, there's no problem. This equation is valid. The problem is that in the inversion region, this equation that we derived last time would not be valid. Instead, out of the three component capacitance, we have to conclude at high enough frequency, this capacitance drops out. Do you know what I mean? Because the inversion layer charge will not respond to high frequency signal. So we will only have those two component capacitance and not this component's capacitance. Okay, let's think about that. Don't think about any equation. Just qualitatively, can you visualize this concept? The accumulation capacitance is there because accumulation charge will respond to changing phi s. Depletion capacitance will be there. Certainly depletion charge will correspond to changing phi s. But inversion capacitance will not be there because inversion layer charge will not correspond to rapidly changing phi s. Is it okay? So now you see the advantage of having this equivalent circuit. Thinking in terms of equivalent circuit, how would the elimination of this capacitance change the CV curve? It won't change this part, won't change this part, only make this part, take away this component. What's left is only C depletion. Is that right? So therefore, it's just this component. Right? So this is our high frequency. You follow what I'm saying? All right. So in this sense, then, low frequency capacitance is the one sort of the more quote-unquote normal, perhaps. Doesn't mean it's more prevalent, all right? But it's the more, shall we say, the simpler of the two CV is the low frequency, because just assume everything is equilibrium. The high frequency requires us to sort of consider that electrons don't respond to varying QS, then we have high frequency. That's good. That's qualitative discussion. Any questions about that? Now, question for you. Quantitatively, how do you deal with that? Do you think you can find expression of CS as function of phi s for high frequency? Somehow? How do we modify the CS as function of phi s that we derived last time such that it's valid for high frequency? What we derived last time is good for equilibrium, or called a low frequency. Low frequency is not a accurate description what we are assuming. So later I would suggest you not to use the term low frequency, but you know what I mean now. Low frequency just means it's a synonym as equilibrium. All right. So last time we derived the relationship between CS and phi s at equilibrium. We have equation. Can you imagine some simple ways of changing that expression so that's valid for high frequency capacitance? Does this make sense? That is, if you can identify in the equation we derived last time, those terms that correspond to electrons, and then we just cross them out, that will give us expression of CS that includes the whole contribution and depletion charge contribution, but no contribution from electrons. Does that make sense? Yeah, at least, approximately. Maybe we have taken away even the equilibrium small concentration of electron. So in that sense, maybe it's not exactly right, but that density is very small. We know it's not a problem, right? So, let's see. How would you do that? Okay, here, just look at next equation. This is what we derived last time. Which terms in this equation do you think have to do with electrons in the substrate? Make a guess. Just make some guesses. Small number is not important, like this n naught times 1 is not important, right? Small number. What significant numbers may be related to the electrons in the inversion charge? This must have to do with that, right? Don't you agree? Right? How about the denominator? This must have to do with that, right? Right? Now, whether you should keep this -1 term or not, maybe you have to think about a little bit to see whether it satisfies some special condition. At flat band, for example, is there something unusual? It should revert to the original flat band situation, right? Condition, for example, right? So that would make sense, don't you think? Okay? Or qualitatively, as I said, if you don't worry about the -1, then just say anything having to do with n naught will go to 0, right? Because another way of thinking this is essentially by assuming that EG is infinity. Okay? If EG is infinity, then we would not have any minority carriers, right? No matter how much bending. So that's another way kind of to think what you would have to do to delete, to change this to high frequency. You follow what I'm saying? All right, good. I actually have never seen this in any textbook, any research papers. But I think it makes sense, right? So this is how you will be able to write down the CV equation for high frequency. Okay. All right. Any questions about this difference between high frequency and low frequency, that concept? Okay. Yes.
Well, the one thing you didn't mention is
yes, I'm listening.
Where the electrons do come from.
All right, very good. Thank you very much. So now let's go back to this low frequency. If we wait several minutes, eventually electron will be created by thermal generation. All right, and one thing we should know is that we should have confidence that equilibrium will always be reached if we're patient enough, long enough that we will reach equilibrium. And right now I can tell you, usually in a typical piece of semiconductor, it will take several minutes for the equilibrium electron to be generated. In other words, if I suddenly apply a voltage to the gate to bend the band to change the bending from 0 to what I just drew on the right-hand side in this diagram, then it's going to take a few minutes for the inversion electrons to appear, to be there. Okay? It will take that long. And the mechanism for generation of electron in a p-type semiconductor is the thermal generation. Okay? Now, having said that, I want to quickly add something, and I think this will remove the pressure on you a little bit to spend too much time about this question about where electrons come from. Where electrons come from in an MOS capacitor indeed is thermal generation. That answer is 100% right. But interestingly, these days in engineering, for engineering purpose, we rarely deal with MOS capacitors. We always deal with MOS transistors. Even when we want to study a capacitor, we just take a transistor and ground the source drain to the substrate and call that a capacitor. That's typically the way engineers work today. All right, not that we cannot get our hands on capacitors, but we actually prefer not to deal with capacitors, because with capacitors we have to deal with the question of where electrons come from. Now, if instead of capacitors we simply go for a transistor and ground the source and drain to the short source and drain to the body. Suppose we do that. Now the electron can come from the source drain region. So the so-called low frequency case never exists as long as we work with transistors. Are you following me? Okay. So this, therefore, that reason, the low frequency case is not that important from engineering point of view. All right. Now, historically, low frequency is kind of an important special case. I take that back. The high frequency, therefore, never exists. We never deal with high frequency case. We always have electrons. Follow what I'm saying? All right. So historically, high frequency, low frequency difference is important because, you know, for many years, researchers had hard time getting their hands on transistors. Short run, getting capacitors is the standard for people to study the physics of MOS capacitor, I'm sorry. So, and certainly in the universities, that's done a lot. But today, you know, if you want to get a capacitor, you have to go to a wafer that contains a lot of transistors anyway. So there's no need to avoid using the transistors. So the standard structure for us to measure CV curve is a transistor, not a capacitor. And therefore, we can get the low frequency CV curve all the time. And that's another reason why this name low frequency could be a source of confusion. I don't like that, low frequency. Another reason I don't like the name low frequency is, suppose we truly have only a capacitor, not a transistor. All right? How low a frequency do you have to go in order for the electrons to vary with your phi s step by step in an equivalent manner? What frequency? Do you want to make a guess? I already gave you a hint. I mentioned something a little earlier that could allow you to answer this question.
60th of a hertz.
That's right. Well, I said it takes minutes for these electrons to reach equilibrium with phi s, right? All right. So if you truly think you can get low frequency CV by using low frequency, you have to get 10 to the minus, 4 hertz or something like that. Now in reality, it's not that bad because it's small signal. We only want to change the capacitance a little bit, change the charge a little bit, not really reaching true equilibrium. So maybe you can get something that looks like that, somewhat at 1 hertz, at 1.1 hertz or something like that. But the shape is going to be very bad, and it's not going to look like this. All right. But it will start showing up. Will start climbing up. All right. And but even 1 hertz today, it's an impractical thing to do, even with expensive CV meters, just because at 1 hertz the capacitive current is so small, right? When the AC current is so small, you're going to have a hard time measuring that with the capacitance meter, because capacitance meter is based on measuring the AC current inside of this meter, and divide that by the AC voltage, and it also look at a phase. It's a vector ammeter, and that's how you get a capacitance reading from the capacitance meter. So when the frequency is low, the capacitance current is very small. You won't get very accurate reading, right? So it's actually never practical to try to get a CV at low frequency. All right. So I don't like the word low frequency, but there's a way to get a curve that's supposed to be low frequency, but it's not measured by applying low frequency. Let me tell you what it is right now, and I think this is an interesting thing. So let's go to page 434. It's called the quasi-static CV. Quasi-static CV is a realistic, quote-unquote, low frequency. As I said, I don't like to use the term low frequency, but it is still commonly used. Instead, when you see a curve like this, I prefer you call this a quasi-static CV. Okay, that will show you really know your stuff. This is a quasi-static CV. That's the theoretical low-frequency CV, but we can never measure by applying low-frequency signal in the CV meter, which is not practical. Instead, we can get this quasi-static CV in the following manner. We take a capacitance. We don't apply an AC signal and try to measure that AC current and get a capacitance. Instead, we apply a linear ramp voltage. Now that's very easy to generate, right? Today's signal generator, we just generate very a simple ramp voltage. Also, this ramp rate has to be very slow. You typically will increase this at a rate about 0.1 volt per 5 second per 10 second or something like that. Do you get a sense how slow it is? 0.1 volt per 10 seconds. All right, very slow ramp. Slow ramp. Now, why do we want to apply a slow ramp? Because ramp that slowly, then hopefully the charge will be at equilibrium with phi s. Is that right? Because we're changing things very, very slowly. Do you follow what I'm saying? All right. If Vg is linearly changing with time, let's call that At. A is just ramp rate, right? Vg is equal to AVT. If so, do you agree a current will be flowing through this capacitor? Right? Because you have a dV/dt. Current is equal to C times dV/dt, therefore is equal to A times C. Do you follow what I'm saying? So if we can measure that current, since we know our ramp rate VA, then we will get C. Yes? Right? The only thing is you say, gee, that current is probably pretty small. Well, let's try to see how small it is, all right? Now, I already told you the ramp rate will be something as small as 10 to the, let's say, minus 2 volt per second. Is okay? What do you think is a capacitance that you can comfortably get, I mean, magnitude, using a test capacitor? What kind of, what's the unit? What value? Not unit, roughly. How many, farad? Picofarad, right? We usually get, several tens of picofarad will be no problem, right? Is that right? Okay, so let's call this 100 picofarad. Let's see what current we get, all right? So, suppose it's 100 picofarad. So that is 10 to the minus 10 farad times 10 to the minus 10 volt per second is 10 to the minus 12 ampere. It's called 1 picoamp. The ammeters we use today, can you measure picoamp? Can we measure picoamp? Yeah, if you're familiar with the HP meters, we can measure picoamp. The resolution is about 10 to the minus 13 picoamp. If you pay extra, you can get even better. Okay. Of course, this still means that you have to be careful with the cable. You cannot have a lot of leakages in the BVC connector and things like that. All right. But routinely in the laboratory, people can set up such that they can measure this current without much problem. As a result, you will be able to measure the CV curve. You cannot do that on very small capacitors when capacitors is too small, but use a somewhat larger size capacitor, test capacitor, then you will be able to measure this. Are you following what I'm saying? Okay. So therefore, this is how we actually measure the quasi-equilibrium capacitance. This is what most people will think as the low-frequency capacitance, but it cannot be measured by using low frequency. All right? All right, good. Okay, another concept of capacitance measurement and something that's usually done in practice is a step change in voltage. This is usually done in the wafer fab. We want to have some monitor to see the quality of the substrate. What is the whether there's an unusually large density of impurity in the substrate. And this impurity may be introduced by contamination of the furnace. We often suspect the oxidation furnace can be dirty or diffusion furnace can be dirty. Sometimes we even suspect clean can be dirty. But when they're dirty, we don't have a convenient way of detecting this contamination. Turns out the most convenient way, not very quantitative, but it's very convenient, almost only convenient way, and therefore is often used, is through some kind of a capacitance measurements. All right. The concept is that if we have contamination, and contamination typically is believed to be metallic contamination, mainly because metallic contaminants especially are electrically active. They can generate minority carriers, therefore increase our leakage current, or perhaps do some other bad things. And if you have some contaminants like nitrogen in the silicon that doesn't do any bad things, well, we don't care about it anyway. So it's these metallic contaminants that often we worry about. So what we do is we look for a decrease in the thermal generation time constant. I'll put it another way, we look for increase in the thermal generation rate. And that will give us an indirect indication that we have contamination. All right? So how can you monitor the thermal generation rate using CV technique? What does the CV have to do with thermal generation? Well, it has to do with thermal generation because it's the thermal generation that creates inversion charge, right? It takes several minutes for the inversion layer charge to be created. Now, if the thermal generation rate is higher than usual, that several minutes may become several seconds, right? Is that right? So that becomes the principle of this test, this monitor, okay? So what you do is you take a capacitor, and why do we need a capacitor? Because monitor has to be fast. If we wait until the transistor is finished, this whole wafer is finished, gee, you have already lost your, $50,000 lot. It's all contaminated, right? So you want to find any contamination early on. For example, right after you have done the well diffusion, or after you grow gate oxide, or something like that, you want to be able to do some quick tests to see if the substrate generation lifetime is very short. If so, you just throw away this wafer, start new ones, and you don't have to throw away the a final whole lot of wafer that may be worth tens of thousands of dollars. You see what I'm saying? Okay. So you always just take a very simple substrate, and maybe with oxide, you may have poly gate at that time. If you don't, you just put down some simple metal dots as the gate. All right? They can be fairly large dots. You don't even use lithography. You just use something called a shadow mask, meaning it's a piece of metal with small holes drilled through that. You put that mask on top of the silicon wafer, or between the silicon wafer and the evaporation source. So you will get some metal dots on the silicon wafer, and that becomes your monitor. Then you suddenly apply a gate from, let's say, what would be the accumulation region of the bias minus voltage. Let's assume this is a p-type substrate. Minus VG would put it into accumulation, right? You suddenly change it to what would be inversion. You see what I'm saying? From minus VG to a plus VG. From accumulation to inversion, suddenly. A step change. You follow? Yes? All right. On a CV curve, where do you expect it? Where would you plot A and B? A is here, that's very easy, right? First, I just plotted a CV for the so-called high frequency. I haven't shown you another case yet. I'll use this to introduce that. This is high frequency CV, is this one containing A and C. That's called high frequency CV, right? You have already seen high frequency CV. So on this high frequency CV, where would you indicate A? A just means we bias the capacitor in accumulation, so somewhere here, right? Maybe here. I don't necessarily mean where A is. A may be here, doesn't matter. Somewhere in the accumulation is where A is. Is that right? Yes? C, don't look at B, look at C. C is we bias into the inversion, and we also have waited a long time. If we did that, that's called a C. Where would we be on the CV curve? It will be this point is C. Is that right? This point. Yes? That's our equilibrium high frequency. Yeah? We wait a long time. Then this is what we get. This is what we expect in the high frequency CV. Okay? When we say high frequency CV, we still have to wait a long time before apply that small signal. If we don't wait a long time, we immediately apply a high frequency signal. We won't even get C. Is that right? Because the amount of bending is also determined by the inversion layer charge. If we don't have the inversion charge, this bend. Okay, I'll just give you the what really happened. What's happening at B then? Let me go to that right away. We apply a voltage to bias the capacitor into inversion, or what would have been inversion, and we immediately apply a high frequency signal and try to measure the capacitance at that point. At that point, we already know the electron will not respond to the 1 megahertz charge. That's given, no problem. But in addition to that, we don't have a DC inversion layer either. The difference between B and C is that at C, we would have that inversion, DC inversion charge, because we have waited a long time. At B, we don't have that DC inversion charge either. At both B and C, the electrons do not respond to 1 megahertz change signal, right? But at C, we got that DC inversion layer. At B, we don't have the DC inversion layer. If we don't have the DC inversion layer, what would this band diagram look like? Band diagram will look like this. If we don't even have DC inversion layer, there's no reason for the band bending to saturate at 25B. Remember the argument why band bending will saturate 25B? Because once it exceeds 25B, there will be so many electrons in the inversion layer, and additional VG will show up in Vox, will be taken up by the oxide voltage, not by phi S. Following what? Remember that? But at time B, at point B, there's no time for this inversion charge to appear, to be created. Therefore, band bending phi S can easily exceed 2 phi B. All right? And this condition will give a name called deep depletion. We have depleted beyond 2 phi B. It's called deep depletion. What that also means, XD can be larger than XD max. Is that right? Yes? What that means is that the capacitance does not have saturate at where the high frequency CV saturate. Will continue to decrease with increasing VG. The more VG we apply, the more the band will bend, and therefore the longer the depletion region would be. Therefore the smaller the capacitance will be. So there are really three branches of CV curve. There's the high frequency CV, the low frequency CV, or better, the quasi-static frequency CV, and the high frequency CV, and finally the deep depletion CV. Okay? Deep depletion is what we're looking at here. Therefore, at point B, we actually don't even get the capacitance C. We get capacitance B. It's smaller than what we will get if we had waited longer. So now we are ready to plot capacitance versus time. Capacitance versus time would be like this. At A, we have very high capacitance because we're in the bias into the accumulation, right? No problem, we have high capacitance. And at B, we got this capacitance. It's here. And after a very long time, along this time axis, eventually the capacitance rise from B to C. So eventually capacitance increase from B to C to a higher value. In between, of course, it's going to rise. We're not talking about the shape. We don't worry about that. And typically, the company may define how long does it take for this to rise to 50% between a point here and a point that you get after it saturates after a while, something like that, right? So this, in a good sample, sometimes actually tens of minutes, that long, that's our sample. And when it gets down to 1 minute, you may use that as criteria saying this is too bad. Okay? All right. Other questions? A variation of this, I would not go into detail. I don't know too much detail about that either. There's one company that sells one equipment that allows you to essentially do this kind of CV technique measurement, basically measurement the capacitance, without actually putting down a electrode. If you just have a semiconductor, maybe with oxide or even without oxide, it allows you to measure CV. The idea is to have use essentially a plasma as the electrode, okay, and use the dark region as the dielectric. That's one way of doing it, if you can imagine. All right. Alternative would be simply putting a piece of metal electrode close to silicon surface with air gap in between. Right? So those are the ways you could even try to monitor the contamination without growing oxide and putting down a metal dots, even simpler. Right? But of course, it's not easy to do that, but it can be done. Okay? All right, questions about CV? Nope? Okay. Let's talk a little bit about something called the charge sheet model. And I'm following the textbook. This section, in a way, is just to take another crack at the idea of trying to find a relationship between phi S and VG, if you will, or Q inversion and VG. Let me put it this way: to find a relationship between Q inversion and VG. This is a particularly interesting relationship. So far, we have QS as function of phi s, no problem, hand down. And we kind of know QS function VG because we can relate VG to phi s. Although the relationship is mathematically complicated, the relationship we're speaking of is this one. This allows us to relate QVG to phi s, right? But it's mathematically complex. In addition, we don't know what is a Q inversion. All we know is QS as function of phi s. Now, among the three components, the Q inversion, Q accumulation, and Q accumulation, Q depletion, and Q inversion, among these three components, Q inversion is by far the most important component to us because transistor operation all based on Q inversion. We don't care too much how many charge are in the accumulation layer given VG or in the depletion layer. We very much care about knowing how much charge is in the inversion layer. So we want to know Q inversion as function of VG is possible. So this section gives us a chance of looking at how can we try to get there. Where we really need this is in the transistor chapter. So in the transistor chapter, we kind of go over this again, but the textbook talk about this in this chapter. So we'll go over this quickly this time and try to sort of. So we're going to see twice this Q inversion model. We call this charge sheet model. Okay. So we already have QS as function phi s, and we know how to translate that Q as a function of VG. Let's simplify this relation. This equation itself is very complex because it's good for all the phi s range. Good for accumulation, good for depletion, good for weak inversion, good for strong inversion. Now even here, I have introduced perhaps a new terminology for you. Perhaps you only heard of accumulation, depletion, and inversion. Even inversion, there are good reasons for us to separate that into two regions. One is called weak inversion, one is called strong inversion. Strong inversion is perhaps where you used to call inversion, namely phi s is larger than 2 phi b. We're in inversion. There's absolutely no question about it. When phi s is larger than 2 phi b, or so many electrons, such a high density of electron, we have inverted the surface. The question is, when phi s is between phi b and 2 phi b, sure, the electron concentration is not as large as 10 to the 17th, but it's larger than 10 to the 11th, 10 to the 10th, and certainly it's larger than the whole concentration at the surface, right? Right? Somewhere here, we may have electron concentration equal to 10 to the 15th. Right? At this point, same phi s, whole concentration will be only equal to 10 to the 5th. Do you say we have inverted surface or we have not inverted surface? We have inverted surface, right? And this, by the way, later we will see is what's responsible for the subthreshold leakage current of the transistor. So it's very common to call this inversion region, but it's in weak inversion region. All right. So this would be the depletion region. This will be weak inversion region. This is strong inversion region. Many times it's still useful to think this whole thing is the depletion region. There's nothing wrong with that. So just be flexible. Depletion region usually still refers to what I drew with this longer arrow still. All right. However, it's very often useful to talk about this as the weak inversion region. Okay, it's weak. Useful to talk about that. So one thing we can do to simplify this complex equation is to say we don't want one that's good for all these four regions. We only want one that's good for these two regions. That's all enough. Because outside these two regions, electron concentration Q inversion is truly negligible. Do you follow what I'm saying? All right. You notice we're not satisfied to only take to limit ourselves truly to strong inversion, because it's very important to know Q inversion in the weak inversion region. That's where we have a very serious problem of subthreshold leakage current of a transistor. So we always want to know the electron density in the inversion layer, even when phi s is less than 2 phi b. We want to know that, at least down to this point. Okay? All right. So what can we do mathematically if we're willing to limit our range of validity only to the weak and strong inversion region? Well, you can obviously, well, of course, try limiting certain things. I would not go through the math with you, but you can imagine you start with the full expression and then say, aha, phi s is larger than 1 phi b, right? May not be larger than 2 phi b, but larger than 1 phi b. Just with that, many of the exponential terms will dominate over some ones, over some other things, and you can eliminate those, right? You can imagine that. If you did that, you end up with this, okay? By the way, another thing you can eliminate by making assumptions, anything having to do with hole density can be eliminated, right? Because hole density will be negligible once they're in the inversion region. So therefore, it's somewhat simpler. Now we believe this now contains two components, Q inversion and Q depletion. Okay? It's a simpler. But this next, we also know approximately out of these two components what Q depletion charge is. Do you know what Q depletion charge? Do you know another expression for Q depletion? Of course you know. It's this equation, right? I've seen this many times before. Q depletion is equal to 2Q Ni epsilon s phi s. Phi s is the band bending. It's okay? All right. This, by the way, is a very good approximation, even though it is to some extent it's approximation, very good approximation. Therefore, we substitute this square root term for that Q depletion and end up with expression of Q inversion. Q inversion is equal to this minus that. All right? So this is the first expression we have seen for Q inversion. Now let me tell you the problem with this at this point is that we don't know how to relate phi s to Vg. That's a problem. We did succeed relating Q inversion to phi s. But phi s is never the independent variable. Phi s is always the dependent variable responding to Vg. So the analysis is not complete until we relate phi s to Vg. Okay? Now that turns out to be the really thorny problem. There's really no good answer, let me tell you right now. And you still see people writing papers a few times a year now. The people are proposing there are better solutions for Vg as function of phi s. Okay? And this problem is particularly interesting recently because in the last couple of years there's a revived interest, or maybe I should say new interest, to develop SPICE models at this level of physics. If you're familiar with the SPICE model level 1, 2, 3, you may have used that in E140, 141. You probably noticed, so when we want Q inversion, all we do is to say Cox equal to minus Vt, is that right? That's all you do. But there's some recent interest to model the transistor more accurately than that for circuit simulation. So for this simulator model development, there's some interest in solving this equation more accurately. Okay, try to find an analytical solution. I can tell you there's no good solutions, so it's still a research problem. Okay, but what are some of the partial solutions? I'll show you in the next slide. A question first.
Question. In the equation 3.55, in front of a QS over C oxide, what is the good sign for the plus or minus?
It's because I made a mistake.
Sometimes it's plus or minus.
Should be minus. I made a mistake. Okay? Kevin, could you change that for me? Correct that. All right? So this equation 3.55, it should be a minus sign in front of this QS over Cox. Thank you very much for correcting that. Thank you. All right. So what we can do in order to find Vg is for given Vg, we iteratively solve 3.55. And there are models used in circuit simulation today that actually does that, iterative solution. It's believed that Motorola and Intel both have models that will, for circuit simulation, that will actually iteratively solve this equation. All right? So for every VG, then phi s is solved. With this phi s solved, will be substituted into equation for Q inversion. Okay, I don't know if it's clear or not. We'll solve this equation here. All right? Of course, this term,
Yeah.
this term will be this term here. Well, this is only one part of that term. This will involve the full three equation term, right? The three component term, holes and depletion charge and inversion charge can all be including that. It's a long expression of phi s involving exponential functions phi s, right? But we can iteratively solve for phi s for every given VG. Once that phi s is found, then we put into this to find Q inversion. Now we know Q inversion for that given VG. See, this is involved iterative solution. Okay, all right. Jane, please.
Excuse me, but yeah, through our equations from 3.50, it should be plus, because you already include the sign in your expression for QS.
I did not, Jane. Now, maybe under some conventions you could say that, but to be consistent with the convention I used in the other lectures, I should clarify that QS is just QS. Positive is positive, negative is negative. We didn't do anything to it. All right. So QS is the charge in the substrate, and the charge in the substrate will create an oxide voltage that's equal to minus QS over COS. Okay.
Oh yes,
That's
in
all.
this case, then the 350 should be minus. Yeah, QS
All
equals
right.
to minus.
Thank you very much. So the mistake are double mistakes. So Jane's right. So if you allow a double mistake to correct, then it'll be fine. But I should have done something else here. Let me think. Yeah. All right. Let me think. In other words, Jane, you happen to know this is this. Actually, all right. It's a thorny problem, you know. Every time we see a square root sign, we have to use physics knowledge to determine what it is, all right? So Jane is pointing out that by not putting a minus sign here, I'm implying that I force the QS to be positive. I certainly don't mean to do that. I actually wanted to keep the sign of all these, all right? All right, so the only way I can think of saving this equation right now, I suppose, is to say that I'm doing this. I don't like it, but I guess I'm doing this right now. All right. So Q inversion can be positive, negative, depending on whether you're talking about P-type substrate or N-type substrate, right? Do you see what I'm saying? So we're not forcing any charge to be positive or negative. So all charge can be either positive or negative depending on doping type, depending on the bias, whether we're in accumulation or inversion. All right? Okay. With that definition, QS, there should be minus sign in front of the QS. Okay? Thanks. So I guess the only way to fix that is this. Certainly, that's not what I want to focus your attention on. It's not this sign here. All right? But I'm glad the sign is clarified. Any questions about the sign? All right, good. So one way is to do the iterative solution, and some people still think that's the best. Others will try to find approximate analytical solutions to find VG as function of phi s. Well, one attempt would be something like that. Let's see. No, I take that back. This chapter does not talk about that. Okay, let's just talk about some other approximations. So what I just showed you is one solution. Using iteration, you can get Q inversion as function of VG. Another thing we can do is further narrow down the range of attention. We even give up the strong inversion, only look at a weak inversion. The textbook does this, all right? It says, all right, suppose we even give up strong inversion. We only concentrate on weak inversion. Weak inversion does have special significance. That is, it is responsible for substrate leakage. Strong inversion is also important because it gives us the transistor IV characteristics. But there in the strong inversion, at least we already have one model for Q inversion, right? For better or for worse, we have this one that we can fall back on. May not be very good, but we have one. For the weak inversion region, we don't have one yet. That does not require iterative analysis. So let's try to find one for the weak inversion. Okay. For weak inversion, then we can further simplify it to this. You can convince yourself. All we did is ignore this one terms and that sort of thing. All right? There must be something wrong here. If the one here already, we could have deleted that. So let me see what is wrong here. Oh, this is outside the square root. All right. This is outside square root, I think. Yeah. Okay. So outside square root, first of all, we inside square root, that one, we take it away. And then because of this term, we find out even this can be neglected. We end up with this. All right? It's approximation. Okay? All right. Now with that, then we found Q inversion is, first of all, very simple relationship with phi s. Let's memorize that. It's very important. The relationship that Q inversion is proportional to square root Q phi s over kt. It's a very useful relationship. This is new relationship we have never seen, and yet it may look trivial. If it looks trivial, it's because we already know ns is proportional to exponential q phi s over kt. We have seen this several times before. But there's a difference between ns and Q inversion. ns has the units of 1 per cubic centimeter. Q inversion has the units of 1 per square centimeter. I'm taking this opportunity. I want you to think about these two units and use that to clarify the meaning of n sub s and q sub inversion. Okay? No confusion, right? All right. So ns is proportional to q phi s over kt. We have known that for a long time. But today, we just showed that q inversion is also proportional to exponential q phi s over kt. It's probably not surprising to you, but it's nice to know this is true. So we're going to use this relationship a lot. All right? So just the total charge inversion layer, not just volume density, but total charge inversion layer is exponential function of phi s in this manner. Not only that, we actually even know the pre-exponential term. I don't expect anyone to memorize it, but it's there if you need to look it up. All right? It's good to know. Okay, if you need the model to know what Q inversion layer is, you not only know it's proportional to exponential q phi s over kt, you kind of know what exponential quantity is. All right? Okay. Let's see, what else? Next would be next. In this regime, we also have a simpler relationship between Vg and phi s. This is how we find a relationship between Vg and phi s in this regime. In this regime, phi s is less than 2 phi b. If phi s is less than 2 phi b, can you tell me the relationship between C inversion and C depletion? Now let me remind you what C inversion and C depletion are. C inversion and C depletion are the components in this equivalent circuit. C inversion and C depletion. Well, I've seen this before. Okay? Now, do you remember the relationships between the two of them when phi s is equal to 2 phi b? At inversion, what's the relationship between these two capacitance? They happen to be equal, right? And I even suggested that's one way to understand why we define the threshold this way. Because depending on which side you are from this threshold, we can either ignore, we say the charge is all due to the depletion charge, or charge is all due to the inversion charge. Is that right? So since we limit ourselves to the weak inversion, what assumption can we make about these two quantities? What inequality sign would you choose? Is C inversion much larger than, much smaller than C depletion? Much smaller, right? So we're going to make assumption that we can ignore the C inversion component. So we end up with only one component here, C depletion. You follow what I'm saying? Yes? Yes? If we only have C depletion, now we can solve the relationship of phi s as function of Vg, because this is really just asking you to solve this, for the band bending in this depletion region, assuming there's no other charge other than the depletion charge in the Q inversion. Remember, in that case, we do have expression for Qs very easily, right? It has to do with square root of Q and A to epsilon s times what? Times phi s, yeah? So if we substitute that into which equation? Into this one, it will be very easy to solve phi s as function of Vg, isn't that right? It's just a polynomial. Is that right? Okay? All right? And if you solve that, you can show something that's like that. Okay? Phi s is some square root function of Vg minus VFB. Obviously, it makes sense because the first thing you would do is you move VFB into the left-hand side, make that the new variable, right? And in order to solve phi s. Is that right? And you end up with something like that using the polynomial formula for the differential equation, yeah? Follow what I'm saying? So it can be done that we can find phi s exponential function of Vg, but it's approximate, only good for a certain range. We're not quite because it's so limited. To be frank with you, this equation is very rarely used. It's not accurate enough for us to really want to use it a lot, and it's mathematically too complicated for one to use it at all. If you want some approximation, you want something even simpler than that. Now, what can be even simpler than that? What can be even simpler than that is this. You can, for example, do a Fourier, do a Taylor expansion of this to linearize phi s with phi g. That's one way of doing it, right? Right? You do that, then there's another sort of interpretation. The interpretation is very good, consistent with this picture, going back to this equivalent circuit with only a capacitor in oxide and a constant capacitance called that C depletion. And C depletion, we assume it's a constant, assume that is equal to epsilon s over 2x d max, assuming that. Now, if we had a constant capacitance, what's the relationship between Vg and phi s? Phi s is the voltage between the two capacitors. Well, it's just a capacitance divider. Is that right? Right? Just capacitance divider, right? Yeah? Specifically, if we apply a certain delta Vg, what will be the delta Vs, that delta phi s? Well, the relationship is just this. That's a multiplier. Let's take a moment to look at that. If we change Vg by delta Vg, then delta phi s will change by this. Is that correct? I'll give you one example. Let's say Cox is infinity. If Cox is infinity, what do you expect the relationship between delta Vg and delta phi s to be? If Cox is infinity, then delta Vg is equal to delta phi s. Is that right? Does that make sense? If Cox is infinity, that's what we got. Is that right? Similarly, if C depletion is infinity, then what's the relationship between delta Vg and delta phi s? Delta phi s will always be 0. Is that right? Right? And that makes sense. Delta Vg is equal to infinity times delta phi s. Therefore, delta phi s has to be 0. You see? So I'm just using this to show you this is the correct equation. You can prove this using your, simple RLC circuit relationship. That's all. There's no physics involved, just a circuit, right? But the result is very important. I want you to remember. The fact is that delta Vg and phi s are related linearly. Second point is that delta phi s is always smaller than delta Vg because this quantity is always larger than 1. So delta phi s is always smaller than delta Vg. Remember that. Delta phi s is always smaller than delta Vg. That makes sense. Delta phi s is always a fraction of delta Vg because delta Vg is divided by a divider to create this delta phi s. And finally, the ratio between the two is this quantity. is 1 plus C depletion over C aux. So we have to remember that. There's a ratio 1 plus C depletion over C aux. Okay? And from those two extreme cases that I reviewed with you, you can always figure out what this form is. Should this C depletion on top, or should C aux on top? Should this factor on the delta VG side or on the delta phi S side? Just from those two special cases, you'll be able to figure out, all right? But just remember the general shape is 1 plus C depletion over C aux. Okay. Why is this important? We can really not say too much about it because it said it's really important for the subthreshold leakage. When we get to subthreshold leakage, we'll use this relationship again. But today, let's just say we remembered that there's a relationship between Q inversion and phi S. It's exponential. And secondly, phi S varies linearly with VG. All right? Okay. Now, in reality, okay, I'll just stay with that. Stop with that. Any questions about this relationship of QS and Q inversion and phi S in the weak inversion region? Yes, question.
On equation 3.58, after you take the square root of e to the beta phi s, shouldn't that be e to the beta phi s over 2?
E of the delta phi s. Oh, I see. I took it out of there, therefore shouldn't this be? Well, actually, clearly it's not. Therefore, I probably said wrong how to make approximations. I bet what it is that this is small compared to 1, not this is larger compared to 1. Why don't we verify that, all right? We're talking about there's an upper limit of phi s. That's the only reason we can make this approximation, as you can see, all right? So let's see whether this component is much larger than 1 or much smaller than 1, what I circled. It's much larger than 1, much smaller than 1, all right? It's not easy, of course. So let's see that. Okay, let's see what are we comparing. We're comparing this. We're comparing Ni exponential Q phi s is one term, right? This one term, right? Or and versus the other thing remaining in this is Ni divided by phi s beta Na square, okay? I'm trying to see what else we can do to make this easy. I think we can make another substitution first. Why don't we do this? We say we do it this way. I know. What do we do now? We do it this way. We make Ni squared divided by Na. We make Ni squared divided by Na, replace that with equilibrium electron concentration, N0. Is that right? Ni squared, I'm sorry, N0 is in the numerator. You see what I just did? I replaced Ni squared divided by Na by N0. Is that right? N naught, the equilibrium electron concentration.
N naught over
Na is still there. I only crossed out the second power, yes. So N naught Na, very good. And N naught times this exponential term is what? What's the physical meaning? N naught times this band bending is the surface electron concentration. So is the surface electron concentration much larger than Na or much smaller than Na? These I'm sure you will be able to find is, it's a factor of 10 or something like that. But these can be orders of magnitude different, right? So let's figure out. Is Ns much larger than Na or Ns much smaller than Na, given this condition, given this range? We are in the inversion, but not strong inversion. So do you expect the electron concentration to be much larger than, much smaller than? Smaller than, correct. Because when it's equal to 2 phi s, we'll be in equal to Na, right? So if we're 0.1 volt less than Ns, the 2 phi b, then will be 2 orders of magnitude smaller, right? So the approximation, therefore, is not to ignore 1. I said that wrong earlier. I'm sorry. That's why you had this question. So instead, this is really what? This 1/2 of this term, right? So it's exponential phi b, not 1/2. Thank you. Thank you.
This question, the same equation.
Yes.
Still, I'm wondering the sign.
Good. Let's work out the sign. I've not been careful with sign. I guess I gave you a apology in advance before. When I only deal with one term on left-hand, right-hand side, I don't worry about sign, plus, minus, because just like he is doing, can always pick this up as error later on at the end. And any times I mentioned when we have A plus B, we have to be very careful about that sign, right? We only have A or B on the whole side of this kind. Let's not worry too much about it, and let's focus on the more difficult question. So for example, I pull this minuses out of the head here, because I imagine, I know eventually, if I'm dealing with a p-type substrate as example, Q inversion is negative. That's easy to know. I don't have to memorize any sign or figure out any sign. Yeah? Okay, it's very easy to know that. Okay. All right. 3.4 is a section about VT, but we already talked about VT from our review of the basic MOS theory, so we don't worry about that. So the final thing, let me just say, is in this chapter something called oxide and interface charge. In a way, this is just a correction to the flat band term. Flat band voltage, we introduced it as the difference between the metal work function and the substrate work function. In short, it's called phi ms. Expanded form will be phi m minus phi s. You all remember that, right? Right? In a reality, and therefore Vg is equal to phi ms plus phi s and plus Qs over Cox. But what if the Qs, as we defined it, we involve Q inversion, we involve Q depletion, will involve Q inversion. What if, accumulation. What if there are other components of charge? Of course, we simply add to this, right? But the definition of QS, we don't want to change. QS has very clear definitions. It has to do with these three things. So instead of changing QS, we simply add them to this equation. For example, you have oxide charge or have interface trap charge. Let's say at the MOS capacitor surface, right at the interface, we have a component of charge. So as far as this impact on this equation, it has no difference as Q inversion, right? As if which has some additional charge, just like inversion charge. But we don't want to change the definition of inversion charge. Inversion charge is a very clear definition. It's responsible for our transistor current later, for example. So we definitely don't want to change those things. So instead, we just add this term here, right? It's much better. Similarly, if I have some charge inside this oxide, what do? Well, we just work out what's the relationship between that charge and Vg. Well, it turns out it has to do with this integration. Now, many of you probably have seen this before. Those that haven't seen it, I'll apologize to you. I just ask you to convince yourself. Leave this as a exercise for the reader. If you find that too complicated, then just don't worry about it. In fact, I often just skip this when I teach, say, EE 130. It's not worth spending that 10 minutes to talk about the distributed charge. Just assume the oxide charge can be modeled as lumped as one sheet near the interface, then becomes the same as Q inversion, all right? But if it's somewhere, the result is telling you is that if it's somewhere in between, if the charge is one sheet somewhere in between, this term would simply become, you guessed it, become a Q of the charge divided by epsilon oxide divided by 1/2 of Tox. Just you expected, right? It's as if the capacitance is only that of half of the oxide thickness. You can imagine that. So the physics of this term is not complicated. The math looks complicated, but we still prefer to make them look like that. The way to do it is to put these two new terms into the lump with this and call that all three things V flat band. Okay, that's one interpretation. Maybe I use too complicated interpretation of this definition. An easier interpretation is the following: is that suppose the band truly is flat, there's no QS at all, but because of Q inversion, we have not Q inversion because of Q interface trap, we do have some charge here. So therefore, electric field in oxide cannot be zero, right? And because of the charge inside oxide, there's also increase in electric field inside oxide. So as a result, we end up with a non-zero Vox. So put it another way, is that when the band is flat, the Vox component is really not 0. And therefore, we have to add that non-zero Vox to the phi ms to figure out the flat band voltage. Right? That's another way to interpret why the flat band voltage is not equal to phi ms, but has to add the oxide voltage induced by Q inversion and add the oxide voltage induced by the oxide bulk charge. All right? Okay. So the result is simple. That is, flat band voltage should really be modified by flat band voltage really is the sum of 3 terms. It's equal to phi ms plus Q inversion charge minus QIT over Cox minus this exponential term over epsilon of oxide. That's all right? So all these together gives us a flat band voltage. All right? Okay, questions about this? All right, if not, we'll stop here. And at this point, we'll take 10 minutes break. After that, we'll hold our first discussion session. And I hope you will bring some questions about the 3 lectures we have so far. Okay? Thank you.